Greetings and welcome to another episode of Alfredo's Code Along. Last time we started a C# code and have a bitboard representation, able to start moving things around in our GUI and have it properly spit back and presented as green spots. Now, this is not a very good chess engine because nothing is stopping me from sneaking in a bishop move on a rook or jump over pieces or even capture our own king. So let's get started with that. We're going to start generating the proper and legal moves. So what we do is just start with a C# code. I'll start with a node in Godot and call it generate auth. This is my lazy way to start these C# classes. You could probably find a better way to do it without creating new nodes. Alright, so once in here, we would like this to be called, this class to be called, and spit back or find a proper function and generate the correct legal moves of a single piece of a selected piece and return it as a bitboard. So everything we'll be using is going to be in the forms of bitboards. How should we do that? All right, let's give it a try and start with rook. So in this representation, or in this code along, I think I'll be coding along in advance, at least a bit more than I'm used to, and then show off what I have in a side-by-side comparison to help you. I think it saves time and makes it much easier to explain code in this way. So first, we're going to use rook as an example. To start with it, we're going to need a few parameters set. First, I think we need the rook position, right, where exactly it is in the board we have. Then we also need a self-board, a bitboard that represents every pieces of the friendly pieces. Right? And we also need an any board. And lastly, this is for housekeeping. I'll tell you which piece is having a move. Okay, so I'll see you in a moment and explain through the code. Actually, before we do that, we need to do a few things in the bitboard class. And for example, we need to have it be able to spit back a whole bitboard in the form of a single U along with all the pieces, right? And then I think I'll just call it two separate functions of get black bitboard and another one called get white bitboard. Simple enough. And as the name suggests, they'll just return the bitboard of the selected piece or select the color back when you ask for it. And how to do that? It's quite simple. We simply take the two variables we have, which is the white pieces and the black pieces, and combine them all and we just return it back. About as simple as that. So we can just do that for each of the U-longs, each individual pieces in the black pieces. All right, combine these bitboard with a OR operation. Do a simple OR equals. And I believe that should return the proper values. All right, and we're going to quickly just copy this, and so I don't have to type it again. Just change this to white pieces. And to confirm that it's working, I think I forgot to change the launch file. I'll be right back. Okay, once it is properly compiled, we can use this test button to carrying all the weight to try out these pieces or to try out these functions. So I think we'll just try a white bitboard to see if that's properly done. And did I do this right? Okay, so let's go back and use the string to see if we have the right turn. Okay, so all right, looks like all the white pieces are highlighted. Make sure the black one is also working. Always test while you're going. So you don't have to go back and fix bugs later on. Okay, looks like everything's properly displayed. Alright, good. Now that we know our display and the return bit boards are working properly, we can get started with the actual generate pass. So we will be right back. Okay, let's see what we have. All right, as expected, all of these values, when I said earlier. Okay, what we have here is the rook position, right? Once you have it, display it. Okay. So when you enter this rook path, when it's being called, the rook position has been saved. Right? We want to know where exactly the rook position is, and we'll just use the indexing of 0, 1, 2, 3, 4, 5, 7, and then all the way propagating up from the lowest bit to the highest bit. And then we have a self board that's passed in. It basically displays what do you have in your friendly pieces. And the enemy board is just the opposite of what other pieces we have. Actually, to demonstrate this, I'll add in a different piece. Okay, I think I'll add a piece of rook somewhere nearby. Let's say we add one to the right of it. Okay. Now we can return to the C# code. Oh. Very good. Now, to calculate the rook moves, when we click on the rook pieces, we want to, well, start testing or calculating which moves are legal. So for the sliding pieces and the more irregular pieces, we have two different ways to do it. I haven't really found a convenient and fast way to do it for sliding pieces, but I do have a few tricks for knights and kings. All right, enough of that. Let's get into rook's movement. So once we have the rook position, we want to calculate all the passes to the up, down, left, right. So we start with the right. If we have rook position +1 in index, in the way we indexed it, we basically just look for the square to the right of it. And these two parameters, or these two checks, are for to see if the rook has moved out of the window of the board, or if it has wrapped around the board. For example, if it was on this square, it has an index of 7, right? Location index of 7. If it's wrapped around the board to 8, when you mod it by 8, it will be 0. That means it's preventing it from moving it to the other side of the board. Now, so if we check this, if we move to this index and we start checking for it, if there's a few checks we need to do. If there's an enemy in there, if the enemy bit is 1, then we just set that as a legal move because you can capture an enemy, right? And then we just break out of this right loop. And if you look for it and you see something blocking the way that is a friendly piece, you obviously can't take it, and then you break out of it. Right? And then if you see an empty square, you simply just add that square into the move. So if we follow the logic here, in here we check, there's no enemy, there is no self, there's no friendly pieces, but we see a empty square, we add it to legal move, and then we keep going to the right, we see a rook, enemy rook. Right, and then we take all that, and then we set the square to a legal move, and then we break out of it, and then we proceed to the left. It is a very similar process. Just be careful, be mindful of which way you're moving and what boundary condition you have. And now if you see a friendly move, well, you're obviously not going to take it, not going to add it to legal moves, and etc. The same will be continued for all the horizontal and vertical moves. All right, now that if we return this should be able to return us a good integer that represents the bit board of the legal moves. Now we have a function. Let's try to call it. Well, first of all, of course, to have a reference to it, so we can call it here. All right, and let's go to on piece clicked, on piece selected. So I think we'll reverse this logic real quick so that when the piece is selected, you'll see why I do this in a moment, we would like to direct it to a onslaught clicked, else we can start going into our logic. Okay, so when the piece is being selected, first change our selected piece pointer into the piece, and then we want to call the corresponding function from the generate path, which the result, remember the result of the generate path is actually a string, integer. And we happen to have a convenient function that takes in a bitboard and then change it into, or set the filters of it. That board filter, I forgot what it's called. Set board filter, and then let's call the generate path and find the corresponding function, which is rook path. Okay, and then we give its required parameters. All right, the first is the location. Since remember I made a mistake, I'll have to reverse the ID that we put in. So in slot ID, okay, piece is the one that is selected, that's been selected. We have the location, and then we take in, well, let's first test it with a black rook. Right, so we'll take the blackboard as, the black bitboard, right, as the input for self board, and then a white board as the enemy board. Obviously, I don't have those yet. All right, so let's set those up. Whiteboard, and simply just do bitboard.call, and remember the one we made, get white bitboard. Okay, and similarly, we can just do the black one here, blackboard, and bitboard.call. Black bitboard. Okay, now we just need another variable that says is black. Let's just set it to true since we're demonstrating with a black rook. Okay, now we have all the correct parameters, the arguments passed in, and let's try it. All right, so now when I click on this rook, right, its proper path, its all available slots should be available. And now obviously I can still move it to other places, so let's restrict it in the onslaught clicked function. Put it. Move piece, yada yada. Okay. So we can simply, for now, just do if the slot state of the slot that we checked on is not a free slot. It is not a data handler dot slot state dot free. We can just return early. That means we don't want to do anything when it's clicked into something that can't be moved. Also, we can turn this off since I don't need to demonstrate it at the moment. All right, now if I click on this, right, if I click on other unavailable areas, we can start moving. Perfect. And now we wanted to obviously clear all the build filter after moves. Let's make a quick and simple clear filter function. So we'll call it clear filter. Clear board filter. Do I have a naming scheme? I do not recall. I think, yes, I do. Good to have one. Clear board filter, and we don't really need any arguments since we just wanted to brute force and clear everything. So simple, we just go to the grid array and make everything into null, which we have a simple and convenient. Oh, I put it in the wrong place. My apologies. So this is a slot scene, or slot script, which has the set filter. The default is actually none, so we can go to GUI and go into here and have a clear board filter. Now we want to call that every time we see we finished moving a piece, which I believe we can just add it right before the piece selected has been set to null. Okay, let's give it a try. Lovely. All right, obviously there are some issues here, right? For example, the position is not properly updated. Oh, because the bitboard of this rook has not yet been updated, and we'll worry about that in a moment. Or now we want to be able to deselect the piece as well, so let's add a quick logic to make sure everything's more complete than not. If input is action just pressed, we can just set it to a mouse right. And if we have a piece selected at the moment, we want to deselect it when we click the right mouse button. So we can just do deselected, selected, set it to null, and call declare blur filter again. Okay, so this should allow us to deselect pieces. Okay, looks good. Looks good. Okay. Very good. Now, obviously, the other things don't really work since every piece I choose is going to be directed into a rook's movement, or is going to be calling the rook path. And now let's start making other piece movements. I'll use a few. I'll skip through the simple sliding ones since it'll be very easy, but I'll definitely spend some time on the interesting ones like the knight. Now what we have is the knight path calculation. The inputs are rather similar. You just want the knight's position and most importantly the self bitboard. Everything else is not used, but it's kept in this structure so that it's much easier to do it in the selection process, and I'll show you in a bit. So how is this done? First of all, we have something called a knight mask. It is simply just the standard mask of all the available spots when the knight in this specific position. Right? And I just did calculated a binary of putting 0, 1, 0, 1, all of that into a converter, and it spit back this decimal string. Okay, so basically when you have this standard mask, every time you have another knight position to calculate, you simply pass in the position and shift it by this standard position amount. Right, for example, if it's shifted to this area right here, it's just a -3, and we'll just simply do a right shift 3 to achieve this location. Right, however, when you do that, there will be wraparound that happens. This and these, right, these blocks will also be selected. So at that point, we just do a quick subtraction. Right, if the knight is within these two columns, for example, these two ones, any pieces of the knight mask that is on the other side of the board, which these two strings are simply just this entire strip. Okay, these two just delete all of squares that's on that, just flip all the bits. And then similarly, on the other side, if the knight is on these two stripped, then we simply just delete all the available moves on the other side of the strip. And then after that, you just check if it's the available spot has any friendly pieces, because we can't capture friendly pieces. We will just flip those bits with an XOR, and then we just return it. So this is the end result you'll see. Pretty simple, pretty nice. I should be able to move if I delete my demonstrations. Okay, let's turn off the demonstration. Would be a better way to do it, but I'm quite lazy. All right, now I should be able to move as expected. Very good. All right, in a similar fashion, we will make our remainder pieces. All right, now let's run through all the rest of the pieces calculation. First, bishop, very simple. In the exact same concept as a rook, but you simply change the vertical and horizontal movement to diagonal movement. just offset it by 1, and everything should be pretty self-explanatory. Just simply get something like this, a good diagonal. Alright, now we move on to queens. Queens is the most simple one. You can see how lazy I am. I simply just called a bishop and a rook path and combine them together. And that should give you the queen path. Wonderful. And then king is, well, exactly the same as knight. In the sense of I have a standard location right here and have all the mask around it saved, and then you just move, right? 9 is this position. And you should be able to have all the available movements for king that way. Pawn is a bit more complicated because a pawn on its starting position for each side, right? The black pawn's on this row, right? The 7th row, and the white pawns, right, on the 2nd row should have 2 movements at start. That means we set the pawn into a special bit. And obviously, if a piece is blocking the pawn, he can't just jump over to the 2nd piece. So we basically check for anything in front of the pawn. If there is, this piece cannot move. And then we have an attack mask. So a pawn captures diagonally, not the movement of the pawn isn't exactly the attack pattern of it. So we check for that in a separate way, a separate attack mask. And then we just combine these two and check for the corresponding ones of if there's an enemy in the attack mask, you can attack. If there is an enemy or a friendly piece in your movement mask, then you can't actually move it. And at the very end, you simply just combine those. Of course, on the edge of the board, you can't have the attack mask wrap around the board, so we'll do a similar thing and deleting everything on one line of the movement. At the very end, you simply combine everything together and return a pawn mask, and it should be able to perform properly. Okay, and as you've noticed, I now can pick a piece and have the right mask selected. What did I do here? Simple. I just went back here and changed a little logic in piece selected right here. May look a little frightening at first, but I'll go through the logic real quick. At first, the exact same thing. We save a few variables of the bitboard that we're calling. All right, we have a white bitboard and a black bitboard. Now, this value, we'll set it in a bit. Okay, so if the piece type less than 6, what does that mean? You remember the piece type here is actually set to the data handler piece names. If it's less than 6, it means it's a white piece. It's greater than 5, it's a black piece. So we just separate that and use the isBlack variable to tell you what piece you've been selected. And then we simply just match the piece type. Once you mod it by 6, the remainder tells you which type of piece it is. Once again, so according to this enum. And then we set the function to call to the string of the function name that we need to be calling from the generate path class, and we just pass that in. Simple as that. Function to call. If it's black, we use the black itself, and if it's white, we use the white itself. Everything else should be pretty standard right here. And once you run it, you should have the effect of the chess engine that I have right here. Movable, selectable, and proper path generated. Now you may notice that when I try to do movement, this knight piece hasn't actually moved in the bitboard representation. The GUI has moved, the piece hasn't moved, but the logic doesn't depend on the GUI. Obviously, it has a backend of bitboard data that's actually saved in this bitboard, which is handled in the C# part. Okay, to properly update the bitboard, let's add a few functions inside the bitboard class. Okay, to basically move something, you just need a remove function and a add function. This should give us the effect of moving pieces. So let's take in the location, and let's take in the piece type to know what we're removing. Then we just do a quick check. If piece type is greater than 5, same deal. Like if it's black or white, so currently it would be black pieces, right? Black pieces. We will simply just go to black pieces, check for the piece, use the piece type to access the correct bitboard, right, the remainder, and we just end with the inverse, which should be able to just remove that piece from us, from the bitboard. They should be rather familiar with this representation now. And if it's a white piece, we just do the exact same thing, but with white pieces. I cannot spell. Okay. So this should do the job, and let's have another one that's add, which should be a very, very similar logic. Add piece. Exact same parameters. Type. And we do the same thing. Check. Piece it is. Oops. Greater than 5. Black pieces. Type. We access the right member, and this time we will actually use a different way to do it. We'll add the piece instead of deleting piece. If the binary operation is a bit confusing to you, I encourage you to slow down and read the logic of the operators to figure out what exactly is going on here, how the bits are being flipped. And let's quickly just add the remaining things. White pieces. Forget to change the logic. That should do it. All right, now let's return to the GD script, GUI parts, and let's actually call it. To separate it, let's move this to here. So under move piece, we'll add in a function called remove from bitboard. Just for housekeeping. Pass in the piece that we're removing and go to bitboard dot call remove piece. Move piece. To make sure it shows up, let's quickly compile it. Good. And then we pass in the location once again because of my mess up, everything's inverted. That's okay. Simple fix. Then we give in a piece type, and we should be good. All right, now to call this. So luckily I have most of these things taken care of. All right, so what's the logic? When we move a piece, we first check the location, the goal location. Right? If there is something in the goal location, there's another piece, enemy piece likely, we will try to remove it from the bitboard. And to do that, we'll access the enemy piece through piece array and the location. This is the goal location, the destination. Right. And then after that, we will remove it from the starting location where this piece is moved from, which can be accessed from just piece. This is the piece we selected. Right, and then at the very end, everything is properly done. We will call add piece. Now that I think about it, I probably don't need to create a different function for this. Well, add piece and pass in required values. Location, piece type. Okay, so now the logic is complete. Let's test it out. Okay, so currently the queen is blocked by this knight. And something's wrong. Index piece dot invalid get index piece debug time. Oh, simple typo. Okay. Think. Do it. Very nice. Now look like the path has been updated properly. Okay, the knight has moved out of the way, and if we move it back, good. Oh, oh dear, something's not right. Okay, let's see what the issue is. Once again, turns out I had a typo here, divided by 5 instead of 6. So the piece movement has, or which piece to be added has not been properly updated. Okay, so I believe this will be correct now. Okay, well done. Looks like it's updated properly. Everything is updating right. Okay. Alright. I think that'll be it for today's video. Tune in if you're interested to see the algorithm part for the minimax algorithm and alpha beta pruning, etc. For the actual automation of it. I'll see you the next time. Cheers.